Last time we took a look at section 11.2, and we're going to finish that section up today. We were talking about curves, polygons, and symmetry, and we had finished curves and we had started polygons, and we're going to pick up in the middle of that. All right, some common polygons. We're going to talk about triangles first. A triangle can be classified by its angles. That's one way it can be classified. So if you have an acute triangle, it's a triangle with 3 acute angles, or you could say all acute angles. If you have a right triangle, it will have 1 right angle. And if you have an obtuse triangle, it will have 1 obtuse angle. And we'll go ahead and label the diagrams that are below, with what they are. The first diagram, what kind of a triangle is that? It's acute. The middle one is right. And for the most part, I'm not going to say guaranteed 100%, but for the most part, your triangles will be marked if they're right angles. So don't look at it and go, well, it looks kind of like it's a right angle. They'll mark them if they are intending for you to believe that they are right angles, okay? And then, of course, the last picture is obtuse. Now, classifying triangles by their sides is not the only way to, by their angles is not the only way to classify them. You could also classify them or describe them by their sides. An equilateral triangle is a triangle with 3 congruent sides. Remember, congruent means equal measure. An isosceles triangle is a triangle with 2 congruent sides. And a scalene triangle is a triangle with no congruent sides. And you have to be a little bit careful about what's not said. It does not say that an isosceles triangle has only 2 or exactly 2 congruent sides. So very technically, while I can certainly write down that this is an equilateral triangle, it's actually also an isosceles triangle. You don't have to like the definition, but it is the definition. It has 2 congruent sides. That makes it isosceles. Now, it's not a very good description for it, right? Because it actually has 3, so equilateral is a better way to describe it, but it is isosceles as well. The one in the middle, however, is only isosceles, right? It has 2 congruent angles marked, so it's just 2 congruent angles. Sides, not angles, sides. And then the last diagram would be scalene. Now, if we were talking about the angles on these, and you were looking at this one, is it acute, obtuse, or right? It's acute. How about this one in the middle? It's also acute, and this one on the end, obtuse, okay? So we could describe triangles in either way. Another common polygon that we're going to be using a lot in this class is a quadrilateral. So I'm going to talk about some different kinds of quadrilaterals, and the first one actually is mentioned as a trapezoid. And trapezoid is one of these things that has different definitions in different books. So I want you to be aware that this is the definition from your book, and if you do ever happen to teach shapes with your kids in your math classes, be careful that you use whatever they use in their book, okay? A trapezoid is a quadrilateral with 1 or 2 pair of parallel sides. The other definition you sometimes will hear is only 1 pair of parallel sides, okay? That's not especially helpful because that gives me 2 distinctly different definitions, and there's not one that's more commonly used than the other, unfortunately. An isosceles trapezoid is a trapezoid with 2 pair of congruent base angles. So the pictures that are in here are actually all pictures of trapezoids. Okay? It's not drawn in, but it is intended that I'll draw it in now. You can mark yours, that these 2 actually have congruent sides, which also means that they will have congruent base angles. If you get one, you get the other one for free. So the one in the middle is actually called an isosceles trapezoid for that reason. And in fact, all the diagrams that I chose to put on this slide have one pair of parallel sides, the top and the bottom, right? So I didn't draw you an example of one that has two pair of parallel sides. So let me draw you one and see if you remember another name for the shape that I'm about to draw you. Do you know another name for the shape? You're close. If they're all congruent, it would be a rhombus. What if they're not all congruent? Parallelogram. So this is why most I'm not even going to say most because I'm not even sure that's true. Some textbooks will not actually use this definition because they don't want this shape to be thought of as a trapezoid. Because we have another sort of image when we think of that one. We think of it being a parallelogram or a rhombus, right? Our definition will include that shape as a trapezoid. All right. The other two images at the bottom are trapezoids as well. So is the one I just drew. So let me write trapezoid in all of them to be consistent. So this would be a trapezoid. And so is this one. And that one. We're going to move on to parallelograms and rhombuses now. So a parallelogram specifically has both pair of sides, opposite sides parallel. A rhombus is a parallelogram that's equilateral. So draw these four shapes in. Are they on your paper? Are they? Okay, good. At one point I didn't have them on the paper. So the first, are they in the right order? Even better. This shape. What can you tell me about this shape? What categories could I put it in of everything I've said before? I already know one of them because I mentioned it a minute ago. It's a trapezoid. What else is this by the definitions that we've looked at? It's a parallelogram. As it's drawn both visually and because it's not marked, is it a rhombus? No, it's not. It doesn't even kind of look like it. Looks like this. The top and the bottom are longer than the sides. If they were all marked congruent, we would say, okay, well, that's just a drawing sort of thing, you know, but they're not. So this one would not be a rhombus. How about the second picture? What is that a shape of? What does it visually appear to be? Anything? Yeah, it looks like it's a rhombus. It's not marked. We'll mark it just for good measure. Your diagrams from your book are better than the ones that I can sometimes pull off the internet. It's really hard to find exactly what you want sometimes, image-wise, when you're searching the web. So it is a rhombus, or at least it was intended to be. What else do you think it is? Well, the definition of rhombus says it's a parallelogram that's equilateral. So if it's a rhombus, then it's a parallelogram. It has to be. I mean, that's part of the definition of being a rhombus, right? So yeah, we get that one too. It's a parallelogram. And take a look at the definition of parallelogram. Parallelogram has both pair of opposite sides parallel, right? Well, what was the definition for trapezoid? One or two pairs of parallel sides, right? So this image is also technically a trapezoid. How about the third image? We want to say rectangle. We haven't talked about rectangles yet. You can write it down if you would like. The definitions of things we've talked about before, what is it? It's a parallelogram. It's a trapezoid. Is it a rhombus? No, it isn't. So this one would be a parallelogram. And it would be a trapezoid. What do you think on that last one? Parallelogram, trapezoid, rhombus, what do you think? trapezoid because it's got at least one pair of parallel sides, and parallelogram because it's actually got two pair of parallel sides. And as long as we're making assumptions, it looks like they're all congruent, doesn't it? Yeah, like I said, your diagrams in your book will be marked. Mine, unfortunately, weren't. But yes, it's all of those. It's a trapezoid, a parallelogram, and a rhombus. And now we have the word that you wanted to use, right? Yes. Rectangle. Okay, so if it's a rectangle, it's a parallelogram with a right angle. And in fact, it's got to have 4 right angles for it to anyway make sense, but it has a right angle. So the images below, are they parallelograms? Yes. Do each of them have a right angle? Yes. So this is what I was talking about last time. I mentioned it in passing and said we'd talk about it later. These images are both rectangles. So if a child looks at this shape that you're going to call a square in a minute and says it's a rectangle, don't go telling him he's wrong. He's not wrong. He's right. It is a rectangle. It just has a more specific name. And that's what we usually want, from our kids to say. But these are both rectangles. So write in there that they're rectangles. Now, a specific type of rectangle is a square. A square is an equilateral rectangle. So by definition, a square already is a rectangle. It just happens to have 4 congruent sides. And again, they're not marked, but they are congruent in that second shape. So the second shape is your square. The first one isn't. It's very clearly longer than it is tall. It is not a square. So a square is both a rectangle, and it's actually also a rhombus. If you take a look back at your definition of rhombus, a rhombus is a parallelogram. Well, a square is a parallelogram. That's equilateral. Well, a square is equilateral. So a square is a rhombus and a rectangle as well. Kite. Kites are interesting. I've got some images up here of kites. A kite is a quadrilateral with 2 adjacent sides congruent and the other 2 sides also congruent. This one's marked really nicely, so I was apparently able to get some good pictures of this one. On the first diagram, this is what you probably think of when you think of a kite, like the flying in the air kind of kites mostly. You've got the left hand 2 pieces marked as being congruent, the right hand 2 pieces marked as being congruent. The second picture, it's joined like second and third sort of together with that same white backdrop. The second picture is much like the first one, right? Very, very similar. The third one is probably not what you would call this. If you were thinking about this particular shape, you'd probably call it something different. Maybe you'd call it an arrow or something like that. It actually fits the definition of kite, however. The bottom 2 sides are congruent, and the top 2 sides are congruent as well. So by definition, it is also a kite. Okay? So what we're going to do next is we're going to take a look at some true-false statements. I'm going to give you a couple minutes to read through them, see what you think, answer true or false. Feel free to look back at things. After you've gotten through, find your partner, most of you are sitting by your partner, and compare notes. If you disagree, talk about it and see if you can figure out a joined answer of which one you think is correct. Okay, let's compare notes all together. You guys have kind of stopped chatting a little bit, so I think you're probably finishing up. An equilateral triangle is isosceles. True or false? True. We actually talked about that one, right? We did. Let's see. A square is a regular quadrilateral. Do you remember what the word regular meant? Nope. 4 congruent sides, 4 congruent angles, or all. In this case, 4 because it's quadrilateral. So does a square have that feature? It does. So it is a true statement. A square is a rhombus with a right angle. What do you think? True. Good job. All angles of a rectangle are right angles. True. The definition said 1, but by the very fact of the way parallelograms are formed and it having 1 right angle, all of them are. A rectangle is an isosceles trapezoid. True, trapezoids have one pair at least of parallel sides that has that, and isosceles means it has two pair, or it has a pair, two sides that are congruent, and it has that. Some isosceles trapezoids are kites. True is actually true. What image did you have in mind? A square actually works. If you have a square, then it is both an isosceles triangle and, isosceles trapezoid and a kite. G, if a kite has a right angle, then it must be a square. That is false. Did you have a picture? Or did you try and make one? Over here, you mean? The one on the left? It does kind of look like that, yeah. So if it were drawn, perfectly, and it looks pretty close anyway, we could imagine that there'd be a right angle there, but that's certainly not a square diagram, right? It doesn't force that to happen. So good job, good job. Well done, guys. All right, this is actually an organizational hierarchy of polygons. I'm going to let you draw it in. I don't think I put it on there yet. You're going to draw for me. This one just includes triangles and quadrilaterals. There, of course, are lots of other polygons. But it gives you some kind of an idea of the relationship between them. So if we talk about the triangle sort of side of this diagram, if a polygon is a triangle, it's either scalene or isosceles. And if it's isosceles, it also has the possibility of being equilateral. So if you see something underneath something else, it means that it's already one of those things. So an equilateral triangle is an isosceles triangle. That's the way that this picture works. If you go and you look on quadrilaterals, there's really only two broad categories of quadrilaterals: kites and trapezoids. By definition, a kite could be a rhombus, and a rhombus could be a square. So that's what's going down here, right? So if I start with square, a square is all of the things above. If I start with a rhombus is a kite, it's a parallelogram, and it's a trapezoid. All right? If I look at the side with trapezoids, a trapezoid could be parallelogram. It's one possibility. It could be isosceles. It could be neither. That's okay. But we can break it down into a couple of more specific diagrams. And if you have a rectangle, right, a rectangle specifically is an isosceles trapezoid. It's also a parallelogram. And then a square is also a rectangle. Kind of like a word picture. All right, we're going to shift gears. This is our last sort of highlighted piece of information in the title of our section, Symmetry. We're going to talk about line symmetries first. A line of symmetry is a line which is its own image under a reflection in or folding along itself. So it's a line about which we can reflect an object and it stays the same. So imagine these three pictures right here. Some of them have line symmetry and some of them don't. We'll start with the easiest one, which is actually the rectangle in the middle. That's the easiest one. The rectangle in the middle has two line symmetries. One line symmetry cuts it in half vertically. The other line symmetry cuts it in half horizontally. Not only does it cut it in half, but if you reflected it across that line, the image would be the same. It's an identical reflection. You could talk about folding half of it straight down on top of itself and having the image line up. Okay? So let's go backwards to the parallelogram on the left. What do you think about the parallelogram on the left? Does it have any line symmetry? Kind of tempting to do this diagonal thing. Yeah, it is. And if it were a rhombus, it would work. But because this one's not a rhombus, it won't work. If I tried to do, you guys automatically, I think, pretty much saw that the horizontal and vertical doesn't work because it flips the angles opposite, right? So if you flipped it, if you tried to do it like this, then the image would reflect down like that, right? Everybody got that one, okay. Let me do the one that sort of looks like it's just begging to be thought of, is like this one. Hang on, I'll move it so that it's more lined up. This is begging to be thought of as a line of symmetry. It really is. But if you actually physically reflect it, it's going to end up looking more like a vertical trapezoid or parallelogram than it is horizontal. It will be tall and thin instead of being shorter and wider. Okay? So this one doesn't work. So there are none over here. How many do you suppose there are over here on my square? There are 4. There are the same ones that are on the rectangle, those 2. And then there are the ones that I was trying to draw on my parallelogram, here and here along my diagonals. So I actually have 4 lines of symmetry here. I have 2 lines of symmetry on my rectangle. Okay, so we're going to work through several examples really quickly of line symmetries, counting the number of line symmetries. Draw them in if you'd like as we go. The first shape is actually a what? Do you remember what we called this last time? It's a hexagon. Good. So a hexagon has actually 6 lines of symmetry. You can do much like we just did with the other ones where you cut through the sides halfway. So you have those 3. You can also do like we did with the square, and you can cut through the vertices. So you get these 3. So there are 6 lines of symmetry for a hexagon, a regular hexagon. How many for the A, the letter A in the middle? 1, right down the middle like that. So there's 1. How many are there for the oval? There are 2. This one's very similar to my rectangle. That was terribly drawn. Let me try again. Not much better. Okay. Pretend like it looks good. There are 2. How many line symmetries are there for the letter Z? There are 0. Doesn't work at all. Okay, diagram E. How many? 1. Where is it? Yeah, it kind of cuts between the 2 arrows like this. There's 1 line symmetry here. And how about the, I don't know, all directions symbol or whatever it is? There are 4. Good job. We have the horizontal and the vertical, and then we have the diagonals. It's actually a very similar diagram to a square in the sense of symmetry. So there are 4 lines of symmetry on that one. Another type of symmetry is called turn symmetry or rotation symmetry. This is a figure where you can rotate it a certain number of degrees and it matches back up with itself. And it has to be less than 360 because you can always rotate a figure 360 degrees. So that becomes an irrelevant fact about everything. So we talk about something having rotational symmetry if it's less than 360 degrees and it matches up on itself. The single point in the middle that you turn around is called the turn center. So if you were taking a look at this diagram, it's like the recycle symbol one over here. The first question is, does it have rotation symmetry? Can I rotate it without going all the way around and it looks exactly the same as it did before? I can. How about the second one, the one that looks like a wheel? Yep, I can. And the third one? Yeah, they all have rotation symmetry. So let's talk about those rotation symmetries. The recycle logo coincides with itself after a rotation of 120 degrees. So you might be asking yourself, how did we get 120? Well, if we went all the way around, it'd be 360, right? And do you see how it looks like it has 3 images that all match itself? That's what's going on. So what's 360 divided by 3? 120. So if I rotated this 120 degrees, I would have the same image. But I could rotate it 120 degrees twice, which would be 120 plus 120, or 240. So this also has 240 degree rotational symmetry. And the turn center on this one is this object that's sort of not even a part of the diagram, but it's in the middle, right? That would be my turn center. So let's do the car tire. To find the amount of the turn symmetry for a figure, you divide 360 by the number of similar or possible rotations you see. Similar shapes or possible rotations. So how many similar shapes do you see in the image of the car tire? 6. You can kind of almost count this, what's, sort of appearing to be the spokes of what's going on. Right here, there's 1. Okay, I need that to be a thinner, just a second. 1, 2, 3, 4, 5, and 6. Those are my 6 different images that are repeating itself. So if you took 360 divided by 60, you would get, I didn't say that right at all. 360 divided by 6, you would get 60 for the rotational symmetry. But you could also do 60 plus 60, which would be 120, plus another 60, which would be 180, which is another 60, which would be 240. It's got 5 rotational symmetries. The number 60 added it to itself up to 5 times. So we're going to find the amount of the turn symmetry for each of the rotational symmetries in these figures. Take a look at the first one. What would be the turn symmetry for this one? 180. So my center of my object, this is the Chevy symbol, right? I'm not imagining that, yeah? This is Chevy? Yeah, okay. I don't really do cars much. Okay, so Chevy. And if you rotated this around itself, that point, like spin it like a spinner on a game board, 180 degrees, it would land on itself. So this one would be 360 divided by 2, because if you will, the left half and the right half, or the top half and the bottom half, are 2 images that are similar. So you get the 180 on this one. What's your rotational symmetry for the next one? Is that Dodge? Is that Dodge? Okay. I don't have these things written down, so I'm just guessing. Dodge? How many similar objects do you see in this one? 5. So if we take 360 divided by 5, what do we get? What is it? $72 maybe? 72. Excellent. How many similar shapes do you have in the last one? 6. So if I took 360 divided by 6, I would have a 60-degree rotation symmetry. Now, I'd like for you to notice that an object can have both rotation symmetry, line symmetry, or neither. So it can have one and not the other. It can have both or have neither. So take a look at this. Well, those objects actually are fine. Which of those objects have line symmetry? The star does. Lots of them, right? Drop in lots of different line symmetries. What about Dodge? Does it have line symmetry? It does. It has 5 of them, actually. How about Chevy? Does it have line symmetry? It doesn't. It doesn't. Okay, we also have something called point symmetry. Point symmetry, a figure that has 180-degree rotational symmetry about the turn center. The turn center becomes the midpoint of a line segment through any point in its image. So this one over here, the Chevy symbol, has point symmetry because it was 180-degree rotational symmetry through the center. There are several different images on here. You can imagine all of them rotating 180 degrees. They all have rotational symmetry, 180 degrees, so they have point symmetry as well. Circles are fantastic. They're amazing. A circle has infinitely many lines of symmetry, each of which passes through the center of the circle. All of the circle's lines of symmetry intersect at the circle's center. The circle has infinitely many turn symmetries, each of which uses the center of the circle as a turn center. And a circle also has point symmetry. A circle almost feels like a square, right? We said a square is a rectangle, and a square is a rhombus, and a square is a parallelogram, and a square is a trapezoid. And we say a circle has all of those symmetries that we just discussed, and infinitely many of them as well. So very, very similar in some of the ways that we describe it.